chemically represented as hydrogen borate, is a weak monobasic Lewis acid comprised of boron, oxygen, and hydrogen. It has been utilized for various applications since ancient times, particularly in agriculture and industry. In the pharmaceutical sector, boric acid is recognized for its antiseptic, antifungal, and antibacterial properties. Its effectiveness in treating infections and its role as a preservative in formulations make it a valuable compound in medical applications. This study highlights the detection of boric acid in various pharmaceutical formulations in the pharmaceutical industry.
The material required for chemicals is boric acid, hydrochloric acid, glacial acetic acid, methanol, ethanol, tetrahydrofuran HF, hexane and double distilled water. For the instrument is UV vis spectrophotometer and analytical balance. Next, the instrumental setup for spectrophotometer. This setup involving 3 steps, which is the first one is set the wavelength to the desired wavelength needed, second set the blank, and lastly measure the sample. And remember, do not touch the part of the cuvette that the light through because the fingerprint can interfere with the absorbance readings.
First solvent is water. To prepare the aqueous solution, it started with accurately weighed 20 mg, 25 mg, 30 mg, 35 mg, 40 mg, and 50 mg amounts of boric acid powder. Each amount was then dissolved in double distilled water to prepare 1 ml of boric acid solution at varying concentrations. It is important to handle boric acid with care. So, wear protective gloves to avoid skin contact that can cause skin irritation. Next, 100 microliters of boric acid for each concentrations were taken and was diluted up to 3 ml with double distilled water. This step ensured that each sample was properly prepared for analysis. Finally, the diluted solutions were used to obtain the UV vis spectra of boric acid in aqueous solution.
For this 20 mg of boric acid was accurately weighed and dissolved in 0.2 mHCl solution so as to get a solution up to 1 ml. This solution was further diluted by taking 200 micro-L of the solution and diluting it up to 3 ml using 0.2 mHCl solution. The resulting solution was used for carrying out the UV vis analysis of boric acid solution prepared using 0.2 mHCl solution.
20 mg of boric acid powder was measured, and then it will be dissolved in hexane to make a 1 ml solution. The solution was mixed by shaking it vigorously for 5 minutes to maximize solubility and will be left undisturbed for 30 minutes to allow sedimentation to happen. Then, the supernatant, which is the clear solution, will be carefully separated from the sediment. Last but not least, 200 microliter of the supernatant was taken to dilute it with hexane up till 3 ml. The solution was then ready for the UV vis analysis.
This is for solubility profile of boric acid in some solvent that includes solvent system, temperature and boric acid percentage by weight in saturated solution. The solubility profile here means how the boric acid solubility changes under varying temperature from different solvents. In this case, the solvent system used are water, ethanol, methanol and glacial acetic acid. From the table, it was observed that methanol and ethanol gives the highest percentage due to different on molecular interactions between boric acid and the solvent's molecules. As we know, boric acid is a weak Lewis acid and fairly soluble in water because proton was not produced, and lastly due to the high temperature. Solubility of boric acid increases as energy overcome the intermolecular force. 2 mHCl solution, ethanol, methanol, glacial acetic acid, THF and hexane. It was observed that water, 0.2 2 m of HCl solution, ethanol and methanol. The solubility was completely soluble, where glacial acetic acid is partially soluble and THF and hexane has very slightly soluble.
Based on the UV-vis spectra, aqueous boric acid solution gave negative absorbance in its UV-vis spectrum except for the concentration of 0.67 mg/ml. This is most likely to be due to the formation of polyborates at higher concentrations in water and thus gave a negative absorbance at higher concentrations. The spectrum also displayed a broad dip with overlapping features. This characteristic is attributed to interactions between boric acid and water molecules. Such interactions can alter the electronic environment of the system, leading to changes in the absorption spectrum.
For UV-vis spectrum of boric acid solution in methanol, the data analysis from the spectrum shows clear spectra without any crowding and also shows positive absorbance where the peaks at the range of 200 nm. This is because the methanol is an alcoholic solution in which also a polar solvent that enables strong hydrogen bonding between boric acid. Also, methanol contains hydroxyl groups where it could be bonded with the hydroxyl group of boric acid. Thus, hydrogen bonding between these two could stabilize boric acid in methanol solution.
Hexane is a nonpolar solvent, meaning it lacks partial charges and cannot form strong hydrogen bonds or dipole-dipole interactions with solutes. Boric acid is moderately polar due to its hydroxyl groups, which can form hydrogen bonds. This polarity mismatch between boric acid and hexane leads to weak interactions between the solute and solvent. Because of this mismatch, boric acid has very limited solubility in hexane. Most of the boric acid remains undissolved, resulting in a saturated solution with minimal boric acid molecules interacting with the hexane solvent. Despite the low solubility, boric acid can exhibit measurable UV-vis absorbance in hexane. This occurs because of weak van der Waals forces between the boric acid and hexane molecules. These weak interactions are enough to allow boric acid to exhibit characteristic absorbance in the UV range, though the absorbance may be weaker and less distinct compared to polar solvents.
By looking at the spectrum given, it is noted that there were positive absorbance and multiple peaks as the data obtained. 2. It explains the weaker absorbance and lack of strong shifts in absorption spectrum. 3. From that observation, it is due to the polarity of the THF itself, which is moderately polar. 4. THF lacks hydrogen bonding and thus limits certain types of solute interactions that would be common in strongly H-bond solvents. 5. Therefore, interaction with boric acid will be less intense and less stable, making it much less preferable to be as the ideal solvent with boric acid.
Next, comparison of solvent. As we know, boric acid is weak acid and primarily soluble in polar solvents. It forms hydrogen bonds and dissolves better in solvents with hydroxyl groups O or similar polar groups. Therefore, based on the solubility on different solvent, we can state that water is the best solvent for boric acid. However, methanol and ethanol are also suitable but less effective than water. And the least suitable solvent is hexane. Hexane is a nonpolar solvent, while boric acid is polar and requires a polar solvent to dissolve. As a result, boric acid is insoluble in hexane. Other solvents like THF and glacial acetic acid are polar but not as effective as water, methanol, or ethanol.
In conclusion, this study highlights the identification of boric acid in various solvents within the context of the pharmaceutical industry. The findings demonstrate that boric acid's solubility and UV-vis spectral behavior vary significantly across different solvent systems. Polar solvents such as water, methanol, and ethanol are most effective for dissolving boric acid, which is crucial for its application in pharmaceutical formulations requiring precise solubility and stability. The analysis also emphasizes the limitations of nonpolar and less polar solvents like hexane and glacial acetic acid, which offer reduced solubility and less favorable interaction with boric acid. These insights are instrumental for optimizing the use of boric acid in pharmaceutical products, ensuring its effective incorporation into formulations for antiseptic, antifungal, and preservative purposes.